start from the beginning, okay? So, are you okay back there? All right, so let's talk about some vocabulary. We just finished a whole unit that was very, very heavy on vocabulary. Put your phone away for me, honey. Somebody tell me, based on the readings, what this word means. What's sample space? It's important to know what it is, because I can tell you, guaranteed, you're going to have to be able to use the sample space to answer questions, and we're going to do that several times today alone. What is it? I'll give you an example of what it is, and then you can tell me in words what it is. The sample space for the sample space for a dice, the rolls on a die are 1, 2, 3, 4, 5, 6. Marcel, what is the sample space? It's a list of all the different possible outcomes, okay? And you have to be very careful that you don't miss any of them, because sometimes when you try to list a sample space or all the possible outcomes, often 1 or 2 are left out. So it's whatever is, every single outcome is necessary is called the sample space, okay? Now there are two different, don't write too much down right now. I'll tell you what's important to write down, okay? Theoretical probability is when each outcome is likely to, equally likely to occur. We have like tossing a coin, rolling a die, and the outcomes are like, in terms of a coin, it would be 50-50. On a dice, it would be 1/6. Each side has 1 out of 6 chances of coming up, that kind of thing. Okay? We already know this because we did this during Flex. What is the sample space of a deck of 52 cards? We have to list them all out. Your test is going to be out here, baby. Okay, so what is the sample space for a deck of 52 cards? All 52 cards. Aren't they all unique? 3 of hearts, 3 of diamonds, 3 of spades, 3 of clubs. And we can go through every single number, every single suit. And so it's 52 individual cards. Would you agree? Okay. And we talked about this last time. We know that there are 26 black cards, 13 are spades, 13 are clubs. There's 26 red cards, 13 diamonds, and 13 hearts. And so we know that. And this is just some basic, it's really slow. Just in case you're watching the video, I wasn't touching that at that time. Okay, so we just know this basic information. So the probability of getting a red card, and again, we did this during Flex yesterday. We know that a probability of what is being asked is over the total, and that's how the notation is P, and then what, bless you, the probability goes inside the parentheses. So, for example, the probability of getting a red card is 26 because there's 26 being asked. There's 26 red cards out of a total of 52, which can be reduced to 1/2. Same thing, probability of getting a club. There are 13 of those out of a total of 52, and that reduces to 1/4. And that makes sense. There are 4 suits, so the probability of getting a club is just 1 out of those 4. Okay. So, what's the probability of getting a king of spades? Well, there's only 1 of those, right? It's a unique card in the deck, so it's just 1 out of 52. Same thing for a 2 of hearts. There's just 1 of those, so it's just 1 out of 52. Now, that was theoretical probability, okay? Empirical probability is sometimes called statistical probability or experimental probability. And just listen right now. You don't have to write these definitions down because I'm never really ever going to ask you the difference between the two. But statistical or experimental probability or empirical probability is determined by an actual experiment. Kind of like if we simulate it, right? If we simulate something, either by flipping a coin or whatever we want to do, that's any kind of simulation or experimental probability is what I'm talking about here. So that the number of outcomes is actually determined by the number of times that you actually do the experiment or actually flip the coin or do whatever. So here's an example. You flip a coin twice. What is the sample space, or what are the possible outcomes when you flip a coin twice? Heads or tails, but the order is going to matter, right? So I've listed them here. The first one could be a head, the second one could be a head. Or we could have the first one being a head, the second one being a tail. Tail, head, tail, tail. okay? When order matters, you have to make sure, and we're going to discuss that whole idea of when does it matter versus when does it not matter here in a little while. But you have to list all the different possible outcomes, okay? So the probability of getting 2 heads, well, it's just 1 out of a total of 4. I've listed, this is my sample space here. Smart board, I gotta tell you. Super slow. That's my, pretend that's a sample space. And we have a total of 4 outcomes, which is why 4 is out of the bottom of the denominator. And there is 1 that has 2 heads. At least 1 tail. Now that's important as a different question. At least 1 could mean 1 or 2. Do you agree? Okay. So when we count those in this particular case, we have 1 or 2. It could be any of those situations. Would you agree? So it's 3 out of 4. Okay. So again, we can use the idea of a sample space when we list all the outcomes and then look at the question and see how many of those fit what I'm asking. Okay? So sometimes listing out a sample space is key. And we know what this is. Excuse me. Rolling a die, I told you what that was earlier. Flipping a coin, etc. The probability of something in the sample space is equal to 1. Or of everything in the sample space, I should say, is equal to 1. Now, let's talk for a minute about when I say probability. We kind of talked about this at Flex yesterday. What can a probability be? We already know it can be a fraction, right? Where we have the total number of outcomes on the bottom and then whatever we're asking in the numerator. So we can write it as a fraction. Well, how else can we represent a probability? We said this yesterday. Cameron? Ratio. And I did ratio, the out of, right? We kind of did that way. That kind of looks a little bit like a ratio. I never want you to say this, because 2 means something different. That actually would be 1 out of 5, not 1 out of 4. And so we get a little confused when we talk about odds and that kind of thing. So I'm rarely ever going to ask you to do that. I might, but it's a rare thing. How else could we write, what did we say yesterday? Remember? Decimals, okay? And actually, the probability of any event occurring can only be between 0 and 1, okay? So a probability, and this is something that's important, so you should write it down. And I'm actually going to make them as a possibility of equaling 0 or 1. When would a probability equal 0? Here's an example. What's the probability that Mrs. Macker is going to have or going to wear a size 13 shoe? 0, because my size shoe is an 8. And I'm done growing, so I'm not going to be able to do that. Okay? So the probability, when the probability equals 0, we can actually attach the word never to it. Okay? So never. The probability that something never happens is when the probability equals 0. Okay? What's the probability? What happens when the probability is equal to 1? It always happens. Okay? So what's the likelihood? And sometimes you'll hear that word likelihood. You probably heard it on your test. That means a probability. Okay? Likelihood, probability that it always happens is going to equal 1. Give me an example of when that might happen. What's the probability that Mrs. Macker is going to go to Virginia Tech at 2:30 today? 1, because I'm getting in the car and I'm headed down to Blacksburg. Okay? It's going to happen, right? So always is when it's going to happen, it's going to happen. There we go. I guess we shouldn't say that. What if I got struck by lightning on the way down? What? What's the probability that, I'm just kidding. All right, so here's an idea that you should have read about in Chapter 13, something called the law of large numbers. And since you guys already read about it, I want you to kind of summarize it in your own words. Somebody tell me what it means. Mm-hmm.
It means that, when an event occurs enough times, it eventually
That's a great way to say it. Settles down to what the actual probability was going to get. If you think about that whole empirical probability, it's based on simulations, right? The more times that you simulate something, the more trials you have, it's going to get closer and closer and closer to the actual theoretical probability, okay? So that's really kind of what the law of large numbers means, is that you really have to do it enough times in order for it to happen. And we kind of knew this with simulations, didn't we? We knew that if we only did a simulation 3 times or 4 times, it's probably not going to be the true probability, right? But the more times you do it, the better you're going to get. Now, some people get confused with this whole idea of short-run behavior. And here's an example of that. Well, let me think of an example of that. Let's say that we're flipping coins, okay? And I flip coins, and I get heads and tails, and I get this. This is an example. Let's say I get heads, tails, heads, heads, and then what is the probability that the next one will be a tail? It's still 50. It's still 0.5. It doesn't matter necessarily what has happened. Even though I have a whole lot of tails, are you thinking that we're due for a heads, right? But it's still 50-50 because each one of these is an independent trial, and it doesn't matter what happens before it, okay? So we have to kind of think about that as well. Yes?
I think it said in the book it's like the coin doesn't know what happened last time.
Exactly. It doesn't have a brain. It can't think what happened, right? Unless it's a not fair coin, unless it's bent or it's somehow manipulated in a way to favor one outcome. But if it's a truly fair coin, and what I mean by that is that one side is not systematically favored, then we just don't know. Okay? Good. Excellent. All right, so just some notations. We already know this. We already know what goes inside the parentheses is what we're looking for. We talk about probability written most often either as a fraction. So in this case, it would be 3 out of 10, or a decimal, or 0.3. And we know that a probability can equal 0, can equal 1, but it must be in between. If I ever get a probability of something is equal to 1.3, and that happened on some of your tests. You told me how likely something was to happen. Some of your answers were like 2.7. What? Why does that make no sense? Because doesn't 1 correspond to 100% of the time, right? So can I ever be more than 100% of the time? No. So if you ever have this, you just know that that doesn't make any sense. And so those are kind of some errors. And you will see that come up. It'll say which one of these doesn't make sense or which one of these cannot be true. Any probability outside of this range would be a red flag. Okay? All right. So we have a bunch of different notations now. And this whole idea of a complement. We talked a little bit about it yesterday during Flex. And you should have read about it too. What's a complement? Julissa, you look really nice today. Is that a compliment? That's with an I though, right? It's not complement like it is in mathematics. So the probability that something will not happen is the complement of that event. And there are a few different notations for that. I believe your textbook uses the C. Is that something you read about? There are other notations that you will see just depending on which author or which text you refer to. So you might see this different in college. And you actually probably saw it in geometry. Sometimes you will see this, the little squiggle. Do you remember that from geometry? That means not. You also might see something like this with a little, it looks like a little L, but it's just like a little square bracket in the top corner. Have you ever seen that before? Okay. Those mean complement as well. Okay? You are here. If you have your homework, I'll take it. Okay? So I will try my best to use the same notation as the book, but I am more of a squiggle girl than I am a C girl. So it's just how, hey, what's up? Notification, someone retweeted. Okay, anyway. Mathematically, what we're looking for is that the complement mathematically is just that you subtract it from 1. Okay? So the probability of an event and its complement together have to add up to be 1. Okay? The probability that I roll a 1 on a die, what's the complement of that? The probability that I don't roll a 1, wouldn't they add up to be 1? Okay? So here's an example. The probability of failing the next statistics test is 0.4, and that is not true. Okay? So I'm not sure where that came from, but no. I did grade your test, by the way. There was somebody who received 100%, so just so you know. Just saying. There were a couple of A's. There were a couple of not A's, too. But you can check School Fusion. I broke it down into multiple choice free response and then your note card. So you'll see 3 different grades. Just add them together. That's your test grade. Anyway, back to this. What's the go ahead, question? So we can visually represent the complement using a Venn diagram where the probability that A happens is what's inside that circle and the complement would just be outside that circle, where we have to add these together because everything inside the rectangle in a Venn diagram is equal to 1. We're going to be using some Venn diagrams. Venn diagrams is a strategy that we will use, especially when we talk about the or and problems. So we'll look at some of those in a few minutes. Did your book have some examples of some Venn diagrams? We'll look at some of those in a few minutes too. So look at this example. The probability of failing is 0.4. What's the probability of not probability of not failing? Let's write that notation a little better there. So the probability that you're not going to fail, which would be fail complement, all right, is going to be what? 1 minus 0.4, which happens to be 0.6. And I do like for you to show that work, just so that I know and you know, we both know that it means complement. You subtract it from 1. Okay? Now, here's an important fact. Oftentimes, it's easier to find the complement than the probability itself. And we'll see some examples of that really throughout this chapter. But sometimes, like, remember how I said that listing all the possible outcomes in a sample space, oftentimes we forget 1 or 2? Well, sometimes if you just do the complement, then you can, the complement is just one thing. And so it's sometimes a little easier to look at it from that perspective. So we'll come across some of those either today or next week. But let's try some questions here. Now, I believe these are some of the questions that you have that I handed out to you. Okay? So you want to get out that piece of paper, and let's at least, we're going to kind of go through these, and not all of them right now, but we're going to kind of come back and forth to them. But let's start here. So we have 40% of cars in our area are manufactured in the United States, 30% in Japan, 10% in Germany, and 20% in other countries. How do I figure out if cars are selected at random, okay, and I just pick a car? How do I find the probability that a car is not U.S. made? The word not is a clue that it's what? That it's the complement, right? So that's your cue word, is that word not, okay? And that does mean complement. So we're going to subtract it from 1. Well, what is the probability that it's U.S. made? 0.4. So what is the probability that it's not U.S. made? Now, that's one way to do it. I could also add up all of the ones that are not U.S. made. I could have said 30 plus 10 plus 20, and wouldn't have that gotten me 0.6 also? So that's another way to do it. You could have done it that way. But remember, sometimes doing the complement it's just one little thing. I just had to subtract it from 1, as opposed to add up all the other parts to it.
So even if it's written like as a percent in the question, you want it in decimal?
A probability means that we're going to never, probability means you write your answer as a decimal. Okay? That's a really good point. Even though the problem had percents in it, your answer, because it's a probability, should be written as a decimal or a fraction. Okay? Good. All right, the next question I don't think we can answer quite yet. So let's come back to this one, and we will after we talk about first of all, when you see this number 2 question, what do you notice? The word or, okay? And or means something, okay? And you read about it, hopefully. Just if you know off the top of your head, what does or mean? One or the other, okay? And we have to talk about what it means to be mutually exclusive, okay, in order for that or thing to happen. Well, I think I talked about it in the next slide, the addition rule. What does it mean? By the way, these 2 words, disjoint or mutually exclusive, mean the same thing. And you need to know both terms, okay? I use them interchangeably. You need to know what they both are. What they both are. So if you think about our car example, what was the second question? Made in Japan or Germany. Okay. Can you be made both in Japan and Germany? No. Okay. So that means that they are disjoint or they are mutually exclusive events. Disjoint events means that they cannot happen at the same time. I can't physically be both in Germany and in Japan at the same time. It's got to be one or the other. And if you have disjoint events like you do in this example with the cars, then you just add them together. It's nothing more than that. It becomes a little bit trickier when they aren't disjoint events. And we did one of those in Flex yesterday, but we'll look at it again. So can we answer number 2? What would I do to get it? We have decided that they are mutually exclusive. They can't happen at the same time, so I know I can just add them together. So what would it be? 0.3 is the probability of Japan, and the probability of Germany is 0.1, so the probability that Japan or Germany would just be 0.4. Good so far? Nothing too hard. So the notation for the word or, and you probably learned this in geometry, is the little u. It does mean or. So in case you see that notation, that means the probability of A or B happening. Okay? By the way, there's 2 Venn diagrams on this picture. Only one of them shows a disjoint events. Which one would show them as disjoint? The one on the left. Good, Joe. The one on the right has something in common. Don't you agree? There is an overlap. So these are not disjoint. Slow smartboard's going to make me crazy. Okay? So let's look at your question. Go ahead, David.
Definition is the same thing for
mutually exclusive? Yeah, disjoint and mutually, they're just synonyms. They mean the exact same thing. And depending on which textbook you read, and I've seen it both everywhere, so it's what it is. All right. So, I want to do not disjoint first. So I'll add here. What happens when you have events that are not mutually exclusive? And I'm just going to write ME for mutually exclusive. Is that okay? Because my smartboard's acting weird anyway. I'm not sure why the smartboard is being so strange. Anyway, not mutually exclusive. What event did we talk about in Flex yesterday, where we talked about two events that were not mutually exclusive? Do you remember it was a card one? Do you remember what example that was? Did anybody? It was a three and, so 3 or red. Remember that one? So probability of 3 or, and I'm going to try to use the notation. So rather than write the word or, I'm going to use the symbol. So 3 or red. Why are these not mutually exclusive? Is it possible to be a 3 and a red at the same time. Since that's possible, they're not mutually exclusive, okay? So you have to decide for yourself when you look at the two events, is it possible for them both to happen? And it is possible here. So if you remember, I think I drew a Venn diagram yesterday. I'll draw it again, officially for notes here. Y'all, I need a new smartboard. So I'm going to draw the Venn diagram this way because they are not mutually exclusive, which means they do have some outcomes in common. What are the outcomes in common? The 3 of, think about the card deck, 3 of hearts and the 3 of diamonds. So I'm going to try to write those here. Do you remember how I did this yesterday? 3 of hearts, 3 of hearts, and then 3 of diamonds. This is amazing, how slow it is. Pretend that it's 3 of diamonds, okay? So what are the others that would not be in the same? We wanted to list all the span. So what do we call the clover again, you remember? Clubs. So we have 3 of clubs. I'm just going to write 3 of clubs with a C. And then 3 of spades. Would you agree? Okay. So 3 of clubs, 3 of spades. And then we have all the other red cards. So I'm not going to list them all, but we'll say all other reds here. And we have, there's 2 2s, 2 4s, 2 5s, 2 6, 2 7s, 2 8s, 2 9. I mean, there's 2 of each. One diamond, 1 heart of each of the other, each of the other numbers. How do I find this probability? Well, if you look at your formula sheet, okay, if you have it handy, you want to get it out, there is a formula that you're going to use. The word or intuitively means we're going to add the probabilities together. That's what we did before. We added them, right? Or means add. The problem is that if I just add both of them together, something special happens, and it's unfortunate. So if I just say the probability of 3, come on, baby, plus the probability of red, what happens? Well, if I do it this way, maybe you can see it. This is the probability of the reds. Oh, good Lord, look at that. And then here's the probability of the 3s. What has happened? I have counted something what? What have I counted twice? The overlap part, would you agree? So I have to subtract one of those away. Venn diagram-wise, the word or means everything on the inside of the circles. That's kind of important. If you're going to write something down, that would be something I'd write down. The word or means you're looking at the numbers or the outcomes inside the circles. Where would the complement be in the Venn diagram? Outside the circles. But when we have events that are not mutually exclusive, and we're just trying to add them individually using the formula, we're over-counting for something. So what I want us to do, well, first of all, I want us to try to write legibly, because that ain't happening. Probability of red. Look at your formula sheet. And if you look, we're going to be in the middle column where it says probability. And that very first formula is what we're going to use here. So let's just rewrite it. It's the probability of A or B. I probably better type in this. This is crazy. I think it's going to irritate me. All right, so it's the probability of A or B. Let me just come back here and type it. Oops. All right, so what is that equal to? If you look at your formula sheet, it says it's the probability of A, which is fine, plus the probability of B, which is fine. But what do we have to subtract? What does it say? in your formula. You have your formula sheet there.
Probability of A and B.
That upside down U does mean and. So it's probability of A, and I'm just going to write the word and because I'm typing it. Oops. Probability of A and B. And it's, oh, good grief, y'all. I need to ask Santa for a new computer. Okay. So that's essentially what the formula is saying. And the A and the B that I'm subtracting off here in the second half of the formula, this part here, is just one of the overlaps, just so I don't count it twice. That's really all we're doing, and that's why that's there. When they're not mutually exclusive, I'm sorry, when they are mutually exclusive, what is this probability? What is it equal to? The A and the B. When they're mutually exclusive, what is this A and B equal to? It's equal to 0. Because if they're mutually exclusive, do we have any outcomes in common at all? So that would just be a 0. So you don't have to worry about it. So let's make this in terms of the context with the 3 of clubs. What's the probability? We have to subtract off the probability of 3 and red. And let's go ahead and fill this in. Oh, gosh. So what's the probability? Let's think about a sample space right now that you're going to get a 3. How many 3s are in a deck? 4. So do you agree that the probability of getting a 3 is 4 out of 52? Right? Plus, what's the probability of getting a red card in a deck? 26, because there's half the deck is red, so 26 out of 52. And I am going to go ahead, I could reduce all of these, but I'm leaving them all out of 52 right now just so I have a common denominator. That's all I'm doing. Okay? And then what's the probability, what's the overlap? How many are in there? How many outcomes are in common? So 2 out of 52. And then we'll go ahead and we'll add these up. What does that happen to be? I believe it's 28 out of 52. Okay? So 28 out of 52 of those cards are either a 3 or they are a red. Do you agree with that? Okay. And you can reduce that, and that would be fine. Excuse me. So, oops. A couple more ideas here before we finish up. The last thing that you guys talked about or read about in the chapter was this whole idea of multiplication. And we're going to talk about the idea of independent with this. Now, independent does not mean mutually exclusive. What was mutually exclusive or disjoint again? It was when the events can't happen at the same time. Okay, you cannot be both in Japan and Germany at the same time. Okay, that's mutually exclusive, that's disjoint. Independent means something differently entirely. Entirely different. Okay? What does it mean for something to be independent?
Like it doesn't affect the thing after it was formed.
Okay? So it doesn't have an effect on any resulting outcomes. One does not affect the other. Let's kind of, before we get to the math part, let's make some decisions as to whether or not the following events are independent or not. If I was going to flip a coin, the flip of 2 coins, are they independent, yes or no? If I flip it once and then flip it twice, is one going to affect the other at all? No, okay? Whether I get a head on the first one will not affect whether I get a head on the second one. They're totally independent, like thinking about them as like separate events. One doesn't affect the other. What about if I'm in an airplane and my left engine fails? What's the probability that the right engine is going to fail? Is one going to affect the other? They're 2 separate engines. It's yes. They are not independent. They are dependent. Why would that be a dependent situation?
Because when one fails, the other one has to work harder and then it breaks.
Right. So when one fails, the other has to pick up the slack, right? And so it's going to have to work harder, and then the likelihood that it fails would be greater. Okay? So that's a kind of just a situational example of when things are either independent or dependent. Okay? Again, not necessarily meaning happening at the same time. That's different. People get these confused a lot. All right, so has no effect on the occurrence of B. If the word is an and, like you see here, we're trying to find the probability of one and the other. The and is the overlap, okay? It is where it is here. And the symbol, by the way, is like an upside down U. I always remember it being the and because I can think about making it into an A, but that's just me. Helps me remember between and or. Okay, but you just simply multiply the events. So let's go back to your sheet here and let's look at question 3. Oh, hang on. That wasn't what I wanted to say. Well, oh, that's fine. 2 cars in a row from Japan. So I have Japan and Japan. Oh, we're going to scrap. Okay, the probability of Japan and Japan. Make sure that you understand that that's what this is saying. 2 cars in a row means Japan and Japan. Are we okay with that? The first one's from Japan and the second one's from Japan. It does not mean or here. Okay? So what would that be? Is one going to affect the other? Not necessarily. Okay? You could probably make an argument that maybe if like my mom has a car from Japan, I'm going to get a car from Japan. So you could probably make an argument about that. But for our sake, we'll assume that they're independent events, okay? What would I do here? Right, multiply. So what am I multiply? No. 0.3 times 0.3. Which happens to be what? Point what? 0.09, right? You can use your calculators if you have them, but it should be 0.09. You're not going to get a 90% chance you're going to see 2 cars in a row from Japan, right? That is a 0.09. You really, when you get a probability, you get an answer in probability, and this is something in habit that I want us to get in practice with, is make sure that your answer seems reasonable, okay? Because sometimes, like if you get a probability that's over 1, don't you know you did something wrong? Okay, so something happened. So we got to think about that and use our answers sometimes to help us, okay? What about number 4? None of the 3 cars came from Germany. None usually means complement. And now we're looking at 3 cars. I like this idea of something called a slot diagram to help us answer these questions. These and questions, and this is something that Mrs. Mackert made up. This is not like something you're going to read in a textbook or whatever, but this is Mrs. Mackert's invention. It's called a slot diagram. If I can write it, it'd be good. It's just a tool to help us find probabilities. If you look at I'll start with question 3 because we already did that one and I can turn it into a slot diagram. In question 3, it said that the first 2 cars that you see were Japan, right? So I'm going to make 2 slots because we're talking about 2 cars. And this works for, by the way, whether it's independent or dependent. It doesn't matter. And we'll look at some dependent events next week. But the slot diagram method will really always work. The first one was from Japan, and the second one was from Japan. And then you just multiply them together. It's really that easy, okay? Let's take this idea with number 4. It said none of the, what?
3 cars.
3 cars. So how many slots am I going to make?
3.
Okay. The first one's not from Japan. Is it Japan again? Germany, sorry. Not from Germany. So I probably have to find that probability. Would you agree? So what's the probability of not Germany? Well, Germany was 10%, right? So it's just 1 minus 0.1 or 0.9. Just to kind of show my work here off to the side. I found the complement. I know what I'm doing. The first one's not from Germany. The second one's not from Germany. And the third one's not from Germany. And it's just a matter of multiplying them together. And what do you get here? I don't know. Cindy has a calculator.
You get something, though.
0.729. Okay. How about number 5? Number 5 says the first Japanese car is the fourth one you choose. Ooh. Okay, sorry, number 5. I read the wrong one. At least one of the 3 cars is U.S. made. All right, so don't write this part down. Just watch for a minute, because there's a hard way and there's an easy way. So I'm going to do the hard way first, but I'm going to show you why this is not the best way to do it. Okay? So how many cars are there? There's 3, right? 3 cars. So we'll say 1, 2, 3. The hard part of this question is the word at least. Okay? This is actually something called a binomial situation, and we'll get to that after Thanksgiving. We're not going to worry about it. We're going to look at it from just a slot diagram perspective. So at least one is U.S. made. Would you agree that we could have just one being U.S. made? Okay, and that one, what's the probability, by the way? 0.4. So would you agree that the first one could be U.S. made? The second one could be U.S. made? Or the third one could be U.S. made? And then what would I fill in all the other blanks? 0.6, because that would mean they're not U.S. made. Would you agree? So we'd have 0.6, 0.6, 0.6, 0.6, 0.6, 0.6. And it's 1 or... You okay so far? The one U.S. made one could be in 3 different places. Well, it says at least one. Now don't I have to worry about 2? So I'm going to redraw my 3 slots again. And I could say, well, it could be the first 2. It could be the second 2. It could be the first and the last. You with me so far? And then what I fill in with the other ones? 0.6s. And again, I'm adding all of this. Would you agree? But then at least 2 doesn't mean it could be all 3 also. Do you see why this is probably not the easiest way to go about doing this problem? How likely is it that you could probably miss one of these? Right? I mean, it's very possible. So this isn't a situation where using the complement is going to help you. Okay? At least one, and this is important and you should write it down for sure. The probability of at least one, anytime you see that word, or that phrase really, I want you to use the notion of complement instead. It's the same thing as 1 minus the probability of none. Okay? That's important. If you look back at all of the outcomes I wrote down here on number 5, the only one that's missing is the 0.6 times 0.6 times 0.6. Don't you agree? That's the only one that's missing. So if I added that one in, wouldn't that be the entire sample space, all the possibilities? So why wouldn't I just find the one little one and then subtract it from 1? That would give me everything else. So it's so much easier to use the idea of complement in this situation. So that's what we're going to do. So at least, what's the probability that at least one of the cars is U.S. made. So I want that at least one is U.S. made. So I want 1 minus the probability that none are U.S. made. Would you agree with that? What's up? I'm loud? It's Friday, dude. I'm going to tech in 2:30. Let's go. I'm excited. I have coffee. I got my tech earrings on. I'm straight out of Stonewall. I'm ready. Let's go. Oh, I'm on recording. Thank you. This is why I need you in my life. Michigan sucks. Did you love my smartboard? Slight distraction. Michigan fans. Anyway, back to the question, okay? What is the probability that none of the cars are from the United States? Didn't we just find that in the question previous? Oh, that was Japan. Never mind. Sorry. Or Germany, whatever. So none from the United States would be, let's find that probability of U.S. complement would be 1 minus 0.4, which is 0.6. Would you agree? So isn't it just 0.6 times 0.6 times 0.6? Okay. And wasn't that the one that was missing from our sample space that we did? And we're just subtracting that from 1. So what is that? Cindy, you're a calculator girl today. 0.6 times 0.6 times 0.6, and then just subtract it from 1. If you do it all in the calculator, just make sure that you do your multiplication first. 0.784. Perfect. But to me, this is a heck of a lot easier than doing this as opposed to trying to put all the outcomes together. Okay? So again, what's the key phrase that told us to use the complement? At least one. Okay? So again, this is what's important here. This is key. And this comes up several times in this unit. Okay? So you have to be able to recognize it. All right, last question, question 6. And then I'm going to have you guys partner up. So question 6 says, the first Japanese car is the 4th one that you choose. So we can still use the notion of a slot diagram here. It's the 4th one. And our first success, we call this, is what's called a geometric probability. You don't care about that yet, but it's coming in the near future. But the first Japanese car we find is the 4th one. So what's the probability of a Japanese car again? 0.3. And so what probability do I fill in before it? 0.7, because those are all not Japanese cars. Would you agree? First one was not Japanese. The second one was not Japanese, and the third one was not Japanese. The first Japanese car was the 4th one. And then you just multiply them together. It's lit, yo. I gotta work on my verbiage. You get me right. Totally. I'm really embarrassed. Actually, my oldest son got angry. He's like, anyway. All right, so what was it, sweetie? I'm sorry, 0.1.
0.129. 0.1029. Sorry.
Okay. How do we feel? We've covered a lot. And we have some time, but I'm going to partner you up for some classwork that I think I'm going to grade, okay, that uses the ideas of the addition rule. What do I have, this is a kind of a recap for a minute, what do I have to be careful of with the addition rule? This is a recap. Whether or not the two events can happen at the same time or are disjoint, okay? What do I have to be, what is going on, y'all? I'm going to just go ahead and stop this.